Hello, everyone. Good afternoon, good evening, welcome. Yesterday we had a wonderful time, office hour. We did a great chemistry. Okay, yeah. This is Sunday. We are going to have the first exam on chapter 3. So we'll cover the material until last week. So if you can, please review it. Okay. And the Sunday we will not have office hour. Okay. We just have a quiz. The same way, send out, you receive it, you do that. Okay. Now open your class notes. Open your class notes, please. Now, what we did last time, we did Heisenberg uncertainty principle. Heisenberg uncertainty principle. And in that set, fundamentally impossible to know precise both the velocity and position at the same time. So this sentence, look at what we have. It is fundamentally possible. To possible know both and at the same time. So that's the word. Now, let's translate this sentence to the mathematical equation called uncertainty principle equation, which is delta P times delta X greater equal H bar divided 2. So that's called uncertainty principle equation. So far, we learned so many equations. Did you remember we learned Einstein equation, photon electron effect equation. We learned Bohr equation. So that's another one. We learned matter wave equation. So that's another one. Heisenberg uncertainty principle equation. Now, in this equation, that's one by one. H bar equal what? And equal H, Planck constant, divide 2 pi. H divided 2 pi. And H, it is Planck constant. See? You get 6.626 times 34 Joule second. And 2 times pi. So you got 1.05457 times minus 34 Joule second. Now, what's the P? P we called linear momentum. P equal m velocity. Delta P, it is a change, or we can say uncertainty. Uncertain equal what? Equal delta mv. M is mass. Mass, it is the quality of the matter. Will not change, so that you get m delta v. Now, what's the mean delta v? Uncertainty of velocity. Okay, now how about the delta x? Delta x, x is a position. So that is uncertainty of position. Now, if we combine delta P and delta S to this equation. So we get M delta V. You cannot see my screen? Can you see my screen, class? Yeah, yes, or probably adjust your computer, okay? Yeah, other people can see it. Yeah, can you probably something wrong? Set up, look at your Zoom setting, okay? And delta x greater equal h bar 2. Now we are going to symbolize delta v delta x greater equal h bar divided 2m. That's the equation. We are going to use it. And that equation we called uncertainty principle equation. So what's it mean? See, basically here is a constant, right? And that one is a constant. So when x, y equal is a constant, when this one small, with this one small, so the change as a small, so which means uncertainty small. Uncertainty is small, which means certain. It is certain. So if you want velocity certain, now the delta x position, big or small, do the math. And this one, big or small, that one should be big. So which means uncertainty big. If you want position certain, small, then uncertainty of velocity should be big, because that's the multiple equal a constant. Now, go to your notes. In the page 38, see, that's the equation you are going to use. That equation, if we say a statement which is fundamentally impossible to know precisely both the velocity and the position. Velocity and the position of a particle at the same time. At the same time, okay? Right? So if you want to know position, where it is, like an electron in the atom. So in that case, velocity should not be certain. If you want the velocity certain, now where is the electron? It's not certain. That's called uncertainty principle, okay? Now, let's do some practice. See, uncertainty position, if very small, delta x small, which means it's certain. Now, uncertainty of a linear momentum or velocity should be big. Go to sample 1. I want you try first. I give you 3 minutes. You try first, okay? Thank you. Thank you. Put a unit. Put a unit, please. Yeah, put a unit. You. Thank you. Okay, I'm going to do that, okay? I'm going to do that. So you look at, so here we are going to estimate the minimum uncertainty of the position. So which means we are going to find the position of the marble, which is delta x. That's the delta x. Now we know the speed velocity within plus minus 1 milliliter per second. Now listen, Heisenberg uncertainty principle, delta x, delta v greater equal h bar 2m. Now the delta x equal h bar 2m delta v. Right, now we know the h bar equal 1.05457 times minus 34 joule second. We know the mass. Where is the mass? 1.0 grams. 1.0 gram, you times 10 to the minus 3, you get a kilogram. You get a kilogram. Now, delta V. Delta V velocity is that, see, it's a plus minus, it's 1.0 millimeter per second. So we need to convert to the SI unit. It's 1.0 times 10 to the minus 3 meter per second. But since here is a plus minus, the maximum uncertainty, you need a times 2. You need a times 2. Why? Because it's a plus minus. Look at. See, now, right? You get a minus and a plus. Minus plus, here it's a minus 1, here it's a plus 1. And the uncertainty should be times 2. That's the maximum uncertainty. See, you got it? So here you need a times 2. Now, you do the math. You do the math. And that uncertainty, it is a 2.6 times 10 to the minus 29 meter. Position meter. And 10 to the minus 29, uncertainty big or small? -1, it's very small. Very small. So in other words, you threw a marble, you will know where its marble go. You will know that. You will know where its marble go. So that uncertainty should be small. Should it be small? You got it? Okay, so any question? Right? That uncertainty should be small. Now go to next one. Go to next one. That's the A. Now go to the B. B is what? The speed of the electron. We confine. What mean confine? Such as here is the size of the atom. Now that electron within the atom, right? So which is what? It is a 200 ppm. Now we are going to find what's the uncertainty. So it's a delta V, delta X greater equal H bar. You divide 2m. Before we are going to calculate, tell me delta V big or small? Big or small? And that one should be big. That one should be big. Why is it big? Because the uncertainty of a position is small. Why? So that's uncertainty, it's here. In this range. 200 picometer, and that should be big. Which makes sense. Okay, let's do that, okay? Delta V equal H bar 2m delta X. Be careful to the math. 1.05457 times minus 34 joule second. 2. Now, we need to find the mass of electron. The mass of electron equals 9.11 times 31 kilogram. Now, when we get this one, we learn this one, the mass of electron in chapter 2. Then you time 200 picometer. So we need to convert to the meter. And that is 10 minus 12. Right? So that you calculate, and that uncertainty of velocity is what? Equal 2.89 times 10 to the fifth power. So you look at this uncertainty, 1 second, it's huge. It's huge. Now, like we did previous times, we are learning science. And when you have the number, we need to understand, at least try to understand what's mean this number. Okay, so look at the first one. In here, see? Where is the uncertainty? Because here. That's the position for marble. Very small, very certain. Now look at the velocity of electron within an atom. And that is huge. Got it? Right? Now, this 2 comes from here, see? That's 2 comes from the equation. Did you see? Did you see here? 2 is come from equation. That equation equal what? Remember, delta x, delta v greater equal h bar 2m. 2 come from here, okay? Now, see, look at the conclusion. 9.11, basically that one is what? Mass, you can use the mass of electron. You can use 0.106 or 109. You can use this one too, okay? 9.109 times 10 minus 31 kilogram. You can get this number in the chapter 2, right? Now, here we cannot times 2. The reason, see, you look at within. What's it mean? Which means the maximum uncertainty, it is a size. Unlike in the first question, you have a plus minus 1. And in that case, the most uncertainty is from here to here, should it be 2? Should times 2? And here is what? Within. But the most uncertain is 200 pm. Now, go to sample 2. 2 minutes. Minutes. Thank you. Put a unit. Yeah, please. Please put a unit, okay. Use 2 significant figure, okay. Good job. Good job. Excellent. Now, in the first question, we did an electron. That uncertainty of velocity speed very big. Now, this time we look at the proton. We look at the proton. We are going to find the minimum uncertainty of the position. So, and this sentence in terms of mass should x. Delta x. Now, and it's a no uncertainty of velocity speed within 3.0 times 10 second kilogram per second. So which is delta V equals 3.0 times 2 kilometer per second. The unit, SI unit, is a meter per second. You times 10 to the third. So I get 3.0 times fifth meter per second. Okay, now the delta x equals h bar divided 2m delta v. One point 0.05457 times minus 34 joule second. Two come from the equation. Now, the mass of a proton, you go to chapter 2, which equal 1.673 times minus 27. Then you times 3.0 times fifth meter per second. Tell me, big or small? That one is very small, very small. Why? Because the velocity is huge and that is a small. How small? You got to do the math, you get a 0.10 times minus 12 meter. I'm going to convert. It's a 0.10 picometer. 0.10 picometer. And we know that the average size of atom is 200 picometer. And that is pretty precise. Uncertainty small. Why? Because velocity uncertainty huge. Go back. Go back, see? If uncertainty position very small, then uncertainty of velocity must be large. It's one number is a small, another one should be big. If one is a certain, the second one should be uncertain. Okay? Right? Yeah. Okay. So last one, before we do the calculation, tell me the minimum uncertainty of a speed of the car. Small, big. Big, small. Okay, let's do that. Some say big. Some say big. Some say small. Some say big, some say small. Let's do that, okay? Yeah, I really want you to do that, okay? I give you 2 minutes. Do that. You? Okay, let's do that. Okay, let's do that. See, at the police monitor automobile and that's the mass 2.0 ton. Now he found within a meter, see delta x 1 meter. So we want to find the minimal uncertainty of a velocity, which is delta v equal h bar 2m delta x. Right? 1.05457 times 10 minus 34 joule second to the mass 2.0 times third kilogram. Right? And uncertainty position is 1 meter. When you do the math, you get 2.6 times 38. 2. minus 38 meter per second. Right? Got it. Got it? Yeah, we should. Now here, this significant figure is very interesting. And here is a measurement. Here is uncertainty. Let's keep it 2. Let's keep it 2 because a meter is not measured, right? So now you look at big or small. That one extremely small. It is extremely small. But that makes sense. It makes sense. Let me tell you. So police gave a ticket, speeding ticket to someone. And then the person said, I'm going to go to the court to argue with the judge. If uncertainty is huge, it's big, such as velocity is 25 miles per hour uncertainty. Now you what? You got it? So now police said you are 80 miles per hour, but uncertainty is 25. Actually, it's you are under speed, not over speed. Got it? So that uncertainty should be very, very small. Indeed, it's very small. Okay? Got it? Oh, the cancel from here, we learned before. Right? We are not going to go back. You go back to the first class. Joule, what's the unit for the joule, please? Yeah, we did it multiple times, at least 10 times. Okay. Yeah, the unit joule. Did you remember? Yeah, go back to review. Yeah, go back to review. Okay. Now, finish this part. So that's the summary. What we did? We did a Bohr model. The Bohr model only apply to the one electron model. When you use Bohr model to solve such as helium, 2 electrons failed. Why? Because Bohr model is based on classical physics and the quantum mechanics. Electron never like a circular. No. You got it? So that we are going to propose two new approach. In that approach, we call it wave mechanics, quantum mechanics. Related to this one, three areas we need to pay attention. The first one is a matter wave. The lambda equal what? Did you remember? H divided what? mv. Right? Lambda, it is a wavelength, and here is a particle. So we did that one. Today I'm going to assign you homework. The second one we did Heisenberg uncertainty principle, delta x, delta v greater equal h bar 2m. So tell us the particle, smaller size, high speed, it is a wave function and also have a particle property. So we cannot determine precisely of a velocity and the position at the same time. We can't. Why? Because that this is not classical physics. The third one we are going to discuss Schrödinger equation. H per psi, E per psi. Right? To solve electron movement, we cannot use classical physics. Use Newton law. Now we have to use a new approach. And the third one is what? Is the Schrödinger equation. We're going to look at the Schrödinger equation. Now, when I learned Schrödinger equation, that's in the college, the third year class. Basically, is what? It is solve a bunch of mathematical equation. Here, we are not ready to do that. We do not have to do that. But I give you some idea what's mean Schrödinger equation, okay? Right? Remember right now, and we know that the matter has wave and particle duality. Particle behave like a wave, have wave property. We cannot know the particle like point like subject. No, we cannot know. We cannot know precise the velocity and the speed. Now, the Schrödinger equation what? And the Schrödinger equation exactly replace the precise trajectory. Now we use what? We use wave function. That's the wave function, see? So to solve this wave function, we are going to find where is the electron. What about the atomic orbitals? Class, some of you, I want you mute. You did it multiple times. Okay, please. I will find out of the class. I want you mute. I appreciate your help. Schrödinger equation basically is what? It's a wave function. It's a wave equation. When we solve this equation, so what we can do? we will get a set of mathematical equation. We solve it. We are not going to solve it, okay? If we are going to solve it, in the future, some of you may, probably not in the high school, in the college, the third year, junior year, you may take that class, okay? So you will get a set of mathematical equation, and that equation we call the wave function per psi. What's it mean per psi? That wave function will tell you the probabilities finding electron in that area. Now, what is the wave function? Change the wave function, it is atomic orbital. Unlike Bohr model is what? That's the orbit. Circular. That's wrong. Actually, what's atomic orbital? Atomic orbital is a wave. It's a wave function that will tell us a pair of electrons or one electron in the atom, the possibility, the probability we find it, and which we call atomic orbital. Okay, remember, huh? Atomic orbital is what? It is a wave function. It is a probability distribution. Find the electron in that area. That's it. So people ask you, what is a Schrödinger equation? What is a wave function? Which is, we can find one electron or a pair electron within an atom, the probability in that area, 90%. That's called wave function. Do I have it? Or in this notes, I do not have it. Later on, I will show you. Now let's show you what's the wave function. Okay, give me a second. I think I will show you. Okay. See? And that is a wave function. So what's this? That's a 1D box. It's a 1D box. We put a cat in a box. Okay. Now, do you need to memorize? No. No, just get the idea. Now, let's go back. Let's go back. Okay. Yeah. I tell you the truth, I forgot how to solve it. I need at least to spend a day, look at the math. How many years I learned? Back to the college. When I was in the junior year, that's one class, half-year class, okay? Chemistry major, everyone have learned it. Remember, the atomic orbital through solve Schrödinger equation, we will get three numbers, and that three numbers will tell us one atomic orbital, okay? Atomic orbital is determined by three numbers or three quantum numbers. Three quantum numbers. How did you get it? You are going to show Schrödinger equation. Are we going to do that? No. But you remember, see, we have a wave equation. Now let me draw a wave equation called h per psi equal e per psi. We are going to solve it so that we will get a wave function which we call the orbital. What is the orbital? It's a probability finding electron in that area. Each atomic orbital, how many numbers? Three numbers. Three quantum numbers. Now let's go to first number. We call the principal quantum number, n. principal quantum number n. And that n, the value 1, 2, 3 all go to integer value. What's the mean n? What's the physical meaning? The n tell us the size of atomic orbital or the energy of atomic orbital. Now, before move on, let's say we learn the Bohr equation En minus 2178 times minus 18 z squared n squared j. Now let's say this n with this n is different. It's different. It's the same n, but it's a different meaning. This n is what? It's orbit. Circular orbit. This n is the principal quantum number. That number, just like this n, you get what? And this one also is 1, 2, 3, go to affinity, right? Go to the affinity. Now it's the same one, but different meaning, totally different meaning, okay? Total different meaning, okay? So that's the one. The same n, all the atomic number with the same n, we said the shell, same shell of atomic of the atom. Now also we introduce shell. And which equal what? It's the same n belong to the same shell, such as n equal 1, n equal 2, 3, 4. Now, and it could be n equal 1, it's S. Why is S? Give me a minute, we're going to discuss. So far, we learned this part. Principal quantum number n. The value is 1, 2, 3, 4, 5, 6. Same n belong to the same shell. That's the first one. Now look at the second one. When n increase, the orbital become bigger. Why? Because n is about the size. About the size. When orbital become bigger, which means electrons spend more time away nuclei. The size. Now go to next one. N increase, which means energy increase. Why? Because n also will determine the energy. When n increase, such as when electron n equal 2, energy higher than electron n equal 1. When n equal 1, energy is lowest. Why? Because n beginning 1. So that we call the ground state. We call the ground state. Oh, you said, yeah, seems like a Bohr model. Sure, but a different meaning. Different meaning. And the Bohr model is based on classical physics. This n solve Schrödinger equation. It's a wave function, totally different, okay? So that's the n. Any question about the n? Any question, please? Okay, now we go to the second number. Remember, each atomic orbital requires 3 numbers. 3 numbers. The second number we call the angular momentum number, L. The symbol we use L, and that number related to the shape of atomic orbital. Yeah, atomic orbital have a different shape. different atomic orbital have different shapes. L, the value from 1 to n minus 0 to n minus 1 for each n. Oh, here's the interesting. Look at this statement. Each n, the value L value from 0 to n minus 1, such as when n equal 1, the L equals 0. Why? Because L equal what? Equal 0 to n equal 1. Each n, L is 0 to n equal 1, because n equal 1, 0, n minus 1, 0. So L only have one value. Now n equal 2. L is 0, 1. Why is it 0, 1? So you beginning 0. You all the way go to n minus 1. See, 2 minus 1 equal 1. Now, L equals 3. What's the number? What's the L? And that should be 0, 1, 2. Look at that. See, L value from 0 to n minus 1. L equal 4. What's the L? Or n equal 4. What's the L? That should be 0, 1, 2, 3. Got it? Okay, now, and we said N, it is a shell. L, we call the subshell. Such as when N equal 1, L only has 1 subshell. When N equal 2, you have 2 subshell. L equal 3, you have 3 subshell. L equal 4, you have 4 subshell. Now, let's move on. N, we use number such as 1, 2, 3, 4. L, we use letter. Why is letter? If L also use number, then we get very confused. We get very confused. But to distinguish N and L, we use number 1, 2, 3, 4, 5, and L, we use letter, but the letter related number, they have a relationship. Such as L equal 0, 1, 2, 3, 4. And its letter is S, P, D, F, G. So if I said E, which means L equal 2. If I said P, L equal 1. If I said S, L equal 0. So that each subshell, we have a symbol such as N equal 1, L equals 0, and the letter called 1S. How do you get 1S? So 1S is that N equal 1, green. L equals 0, L equals 0, which is S, 1S. Now, 2 0, which is 2s. 3, 1 is 2p. 3, 0, 3s. 3, 1, 3p. 3, 2, 3d. Now I want you finish 4. Now do that. Finish 4, please. Very good. Very good. Now, class, very, very good. Now, listen. Some of you, please, I really want you mute. Please. This has happened many times. That should be 4s, 4p, 4d, 4f. Got it. Got it. Okay. Now, see. Orbital of the shell with principal quantum number n. How many groups? 3 groups. See, n equal 2, you have 2 groups. N equal 3, 3 groups. N equal 4, you have 4 groups. N equal 5, you have 5 groups. So identify by L. So we call the subshell of the shell. Now, L is the shape of atomic orbital. We are going to learn that. Okay, right? That's the second number. Now, let's do some practice. Can we go to sample 1? You try it, okay? You try it. I give you 2 minutes. You try it, okay? You try. You. Good job. Good job. Okay, I'm going to do that. Class, it did very well. See, look at the principal quantum number n equal 5. N equal 5. And L equal 0, 1, 2, 3, 4. From 0 to n minus 1. Now we said n use number, L use letter. So here it's S, P, D, F, G. If we continue such as 5, it's H, such as 6 equal I. However, as we will know down the road, we will not use orbital beyond G. We're not, okay? So that in this question, we call the subshell the shell. Give the name. The name, how many subshell? When n equal 5, you have a 5 subshell. So which is 5s, 5p, 5d, 5f, 5g. So you have 5 subshell. And each subshell, what's the name? 5s, 5p, 5d, 5f, 5g. Okay, right? Any question? Okay, now we will come back to this question. Let's finish the third number. So we finish the second number, huh? Next number, magnetic quantum number. And that number, we use a symbol ML. Okay? Magnetic quantum number. So what's the mean that number? So that number is within the subshell. How many orbitals? So what do we do? Now, slow down a little bit. By self-shielding equation, we get n. We get n. N is what? It's a shell. Within a shell, we have a multiple n subshell. In a subshell, we have different number of atomic orbitals, which is ML. How many? Well, minus L, 0 plus L. Now, we'll come back here. See, within a subshell, the number of atomic orbitals is a different one. ML, what's mean? Which means the orientation at atomic orbital in the space. The value, see, is minus L to minus L, including the 0. We can do simple math. In a subshell, how many atomic orbitals? It's n squared. We are going to discuss in a minute. Now, I'm going to do that, okay? I'm going to do that. You make notes. I'm going to slow down. Some say, can you slow down? Yes, I'm going to slow down. N equal 1. L equals 0. Why? Because here is 0 to n minus 1. For the n, it's what? 1, 2, 3 to the n. Now, for the ML, it's what? It is minus L, 0 plus L. I'm going to highlight here, okay? And I want the class, you are going to work with me. So when n equal 1, this one is, see, n subshell, because the subshell is L, right? L equals 0. Why? Because 0, beginning 0, n minus 1 is 0, just 0. Can you tell me ML? Tell me what's the ML, please? And that one is 0. Only 0. Because L equals 0, minus 0, 0 plus 0, just 0. Got it. And that name we called 1s. 1s. How many orbitals? How many orbitals? I write it here. Number of atomic orbitals. Only 1 orbitals, right? There's only 1 orbitals. Good with me? Because there's only 1 value, 0 value. Okay. Good job. Good job. Now I'm going to do n equal 2. What's the L? N equal 2. N equal 2. L should be 0, 1. Why? From 0 to n minus 1. See, 0, 2 minus 1 is 1. No 2. No negative. When n equal 1, ML equals 0. Oh, no. When L equals 0, ML equals 0. L equal 1, ML equal what? And the minus L is minus L, 0 plus L. Not 3, it's minus 1, 0 plus 1. Right? Now, how many orbitals? Here it's 1. Here it's 3. 1 plus 3 is 4. Now, n equals 3. What's the L? And it's 0, 1, 2. L equals 0. ML equals 0. L equal 1. ML minus 1, 0 plus 1. L equal 2 minus 2 minus 1, 0 plus 1 plus 2. How many orbitals? 1, 3, 5. You add 9. Now n equal 4. L equal 1, 2, 3. No. Sorry, not 1. Miss 1. Uh-oh. Zero, 1, 2, 3. Right? So 0 minus 1, 0 plus 1, minus 2 minus 1, 0 plus 1, plus 2, minus 3 minus 2, minus 1, 0 plus 1, plus 2, plus 3. So you get 1, 3, 5, 7. You get 16. Now, so here I said 1 square, 2 square, 3 square, 4 square. It is n square. Do you see? Cool, huh? Any question before move on? No, I want to stay here a minute. Basically, it's what? It's a number game. We play game, we play number. But that has a law, step by step. See, from n shell, how many? You have n subshell, different L. And within a L, you have number of orbitals. And how many orbitals should equal 2L plus 1? Do the math. In a subshell, number of orbital is 2L plus 1. In the subshell, it's n squared. Right? 0 to n equal 1. That's the L, okay? Very good. Now we've done it. So we finish these 3 numbers. Each atomic orbital requires 3 numbers. Now we are going to do some practice. Which question? Oh, I want you go to 43. I want you to question 2. I'm going to give you a little bit more time, okay? I give you 2 minutes. So look at what's the strategy. Thank you. You. Good job, Emma. Okay, I'm going to do that. Class, most of you get a perfect. So the question said assign quantum numbers, not only one number s, for an orbital. Give the possible combination for 4p. Now, the strategy is that the principal quantum number n give the shell number. In this case, n equals 4. The angular momentum number L, that's the L, determined by what? By P, because the P, L equals 1. The magnetic quantum number ML, and that one is related to orientation, spatial orientation of the orbital, which will be minus L, 0 plus L. It's minus 1, 0 plus 1. So how many combination? The combination is N, L, M, L. I want to use a table format. So here it's a 4, here it's a 1. Could it be minus 1? That's 1. 4, 1, 0, 4, 1 plus 1. You have a 4, not 4, I have a 3 combination. Now, each orbital by 3 number, that orbital we call the P minus 1. Here it's a P0. Here it's a P plus 1. So you have 3 orbitals. The 3 orbitals. Right? Oh, the question said why L equals 0? Because of the P, right? Because of the P. L equals 0. Did you remember? No, let's go back. So we said S, P, D, F, G, H. So which is what? L equals 0, 1, 2, 3, 4, 5. When you see P, which means L equals 1. Right? When you see 2, D, L equals 2. When you see F, L equals 3. See, L use letter, okay? Right? Now, how did you know you get a plus 1, minus 1, 0 plus 1? Because that's the ML. ML is what? It's minus L, 0 plus L. Right? Do you see? ML is minus L, from minus L to plus L, including the 0. Of course, that's the definition. Let's go back. That's the definition. See? Integral value between L minus L including the 0, which is L 0 minus L. Very good. Very good. Now, can we go to sample 1? May I give you 2 minutes? Thank you. Thank you. Okay, I'm going to do that. I'm going to do that. Okay. I'm not only to do that, but also I'm going to very detail. I'm going to give it a table. Okay. I'm going to get table. See, with this one possible, yes. Why is it possible? Now I'm show you. Okay. I'm going to just play the number game. Okay. I'm going to play the number game. It's basically it's a combination. It is a combination. Okay. Now let's look at. So n equals 3. Let me write it here. Okay. N equals 3. And L should be 0, 1, 2. Okay, that's good. So n equals 3, L 0 is okay, 1 is okay, 3 is okay. So right now look at the ML. When L equal 2, ML is -2 minus 1, 0 plus 1 plus 2. Now you have a 2, that's okay too. So that's it's okay. Any question? Any question, please? Anyone got it? Okay, now go to B. N equal 4. L 0, 1, 2, 3. N equal 4. L equal 3. That's good. That's okay. That's combination okay. Now ML, when L equal 3, ML is a -3, -2, -1, 0, +1, +2, +3, +4. No, that's not okay. There's no 4 here. That is not okay. Go to next one. Go to next one. N equals 0, that's not okay. Because N beginning what? 1, 2, 3. That's not okay. So this is not okay. Now go to this one. N equal 2, L equal 0, 1. Here it's L equal -1. That's not okay. See, L cannot be -1. Yeah, A is good. B, C, D is not. Any question before we move on? Any question, please? Fun, huh? Yeah, it is. It is fun. Basically like a number game, right? You put the number, you put the letter, you do the combination. It's a combination. Okay, now let's do two. Give you 3 minutes, okay? Yeah, question ask, okay? 3 minutes, okay? Very detailed. ，Thank you. Yeah, 1 more minute, okay. Good job. Good job. Okay, I'm going to do that, okay. Yeah, I want everyone making notes, okay. And for the A, how many value L in N equals 7? That is a shell, right? L is a 0, 1, 2, 3, 4, 5, 6. There was 7 value, see? N equals 7, you have a 7 value. So which means you have a 7 subshell. Now go to the B. How many value ML when 6D? 6D, which means N equals 6 L D SPD, that equal 2. So in order to get ML, you should know the L, right? So ML minus 2 minus 1, 0 plus 1 plus 2. You got it? Now go to the C. How many values 3P? So which means N equals 3, L equal 1, ML equal minus 1, 0 plus 1. Now go to D. n equal 4, how many subshells should it be 4? N equal 4. And let the subshell L equal 0, 1, 2, 3. And let the subshell should be 4S, 4P, 4D, 4F. There were 4 subshells, have a name. Any question? Any question, please? Question, please. The name, we said the name is what? L use letter, right? L use letter. See, S, P, D, F. Now, N use number. So let's get such as N equal 4, L equal 0. That name should be 4S. If N equal 4, L equals 3, and that should be 4F. Which one use? Which one use? See? Right. If you L equals 3, that's the 4F, right? Got it? Yeah, that's the use. See, remember, if you see the F, which means L equals 3, you know the L equals 3, which means it's F. They have related, but we do not use 3, okay? Right? Okay, so now let's look at this C. C is a 3P. Right? When you see 3P, P is L equal minus 1. How do you get ML? Which means it's minus L, 0 plus L, minus 1. Oh, no, L equal 1, plus minus 1, 0 plus 1. Okay, now go to sample 3. A minute. A minute. Okay. Remember, principal quantum number n, that use number. Angular momentum quantum number L, that use letter. But letter with number has a relationship, such as S, when you see S, which means it's 1 at 0. When you see P, it is 1. When you see D, it's a 2. When you see F, it's 3. Okay, right? So A, 6P, N equals 6L equal 1. B, 3D, N equals 3, L equal 2. C 2p, n equal 2, L equal 1, D 5f, n equal 5, L equal 3. Any question before we move forward? Go to the review. Any question, please? We accomplished a lot today. We finished Heisenberg uncertainty principle. We discussed Schrödinger equation with atomic orbital. We did by solve Schrödinger equation, we get 3 numbers. We find the relationship with these 3 numbers. Number game. Now we done it. So we finish. See, atomic orbitals are designated by quantum number NL, ML. And N is the shells, L is the subshells. Right? See? The name, quantum number, okay? The name, principal quantum principal quantum number N, symbol is the N. Value 1, 2, 3, 4 is belong to the shell. Related energy and the size. Angular momentum quantum number L, value from 0 to n-1 for each n. That belong to the subshell. L related the shape of atomic orbital. We are going to discuss next Monday. See, L use letters 1s, 2p, 3d, 4f, 3f, 4g. Next one, magnetic quantum number ML. And in the subshell, how many orbitals? That orbital should be 2L plus 1. Why is it 2L plus 1? Because minus L plus L in the middle have a 0. See? 0, minus 1, 0 plus 1. Minus 2, minus 0 plus 1 plus 2. Minus 3, minus 2, minus 0, plus 1 plus 2 plus 3. And that is 2L plus 1. Y plus 1, see? Right? And that related orientation, such as ML minus 1, 0 plus 1. So orientation is different. We are going to the next class. Next class, we can do that. Okay. Now, of course, all these 3, it is atomic orbital. The first number, which is a spin quantum number, and that related to electrons. We are going to finish next class. We are going to do that. Okay. Now, see, here give you the example. N equal 1, L equal 0. ML equals 0, 1s. N equal 2, see the color, different color. L equals 0, 1. So it's SP. The 2s, 2p, but ML have 3, has 1 here. Again, N equals 3 subshell, which is SPD. Belong to 3s, 3p, 3d. In the s orbital, only 1. P orbital, 3. 5 D orbital is 5. I'm going to repeat. S orbital, only one orbital. P, you have 3 orbitals. D, you have 5 orbitals. F, you have 7 orbitals. Any question before move on? Any question? Olivia, any question? Spin we'll discuss. Spin, electron spin we'll discuss. Not now, okay? Yeah. Olivia, do you have a question? Zoe, do you have a question, please? Or you do not have a color, then you get a color printer, okay? Anyone has a question, please? No question, we are going to move on, okay? We are going to move on. No question, we are going to move on. Now, this particle in 1D, one-dimensional box, we are not going to discuss now. In the future, we are going to discuss, not right now, okay? Yeah, basically it's what? It is a wave function. It is a wave function. Solve this one. Actually, even in the future, I'm not going to solve it. So you solve, see, what's this? That's the wave function. That's atomic orbital. Yeah. It is, but we need to discuss this one in the future. Energy. See, look at it here. It's a wave function. Look at it. Look at the energy. In the future, we're going to discuss. Okay, now I'm going to discuss the shape. Shape and the energy. Tell me, class, which number determines the shape? Which number determines the shape? N or L or ML? L determines the shape. L determines the shape, not N, not ML. It is L determines the shape. Different L have a different shape. Okay. We learned it. We just learned. Now, what's the orbitals? Not the circular. Okay, please change your mindset. It is the probability of distribution of the electron. Such as S orbital. What's the mean S orbital? Which means L equals 0. That's the S orbital, okay? S orbital, it is a sphere shape. 90% total probability. See, here is S orbital. Not 90% probability, 10% in far away. See, and that one, it is S orbital, okay? Now, we are going to discuss the node. What's the mean node? N-O-D-E. It's a 0 probability. 0 probability. What's the mean 0? Look at the mass. Look at the mass. Look at the mass. I want to look at this wave. So in the top is a positive. Here is a negative. Can you tell me where is the 0? Am I right? Am I right, class? Yes, here is a 0. Right? See, here is a 0. In other words, here is a 0. What's the mean 0? Find the electron in that area. Find the electron in that area. It's a probability. Probability is 0. Right? see, here is a 0. Here is a 0. Here is a 0. And we said atomic orbital is a wave. It's a wave function. So in this one, it's a positive. In here, it's a negative. From positive to negative, it's a 0. Okay, now let's go back. So what's the mean node? NODE. Zero probability finding electron in that area. Now, I'm going to look at, here is 1s. 1s, do you see? Here is 1s, here is 2s, here is 3s. What's the difference? Can you tell me 1s, 2s, 3s? What's the difference? Can I say the size? 1s smaller than 2s and smaller than 3s. Agree with me? Right? So why? Because n equal 1, 2, 3. N is what? Principal quantum number is the size and energy. See, 1s is very small sphere. The 2s, look at, that's the 1s, 2s. Between 1s and 2s, did you see the white ring? Did you see the white ring? Okay, how many? 1. Now look at the 3s. How many white ring? 2. Now 3s, 2s, 1s, 0 ring. And that ring, this one we call the node. We call the node. So in other words, for the s orbital, the node is m minus 1. M minus 1. Okay? Very easy. See? Very easy. Look at. See? For s orbital, it's m minus 1 node. Okay? Aha! Now, see? What's this? That's a 2D structure. Here's a 3D. 3D. Look at. So here is 1s. And here's a 2s. Between here is a ring. That's node. Here, how many? You have 1 node, 2 nodes. You have 2 nodes. You have 2 nodes. We finish it. We finish it. See, 1s, 2s, 3s orbital. Or it's a spherical. The different is the size. The different is the size. And now, in the first time, we introduce the node. The node, go back, because it's related to wave. See, here's a node. Here it's a node. Which means the mathematical value equals 0. 0. 0 probability finding electron. Okay. Okay. Now, let's look at the p orbital. We finish S. Can you tell me what's the p orbital? What's the mean p orbital? L equal 1. ML equal minus 1, 0 plus 1. How many p orbitals? P has how many orbitals? 1, 2, 3. 1, 2, 3. Minus 1, 0 plus 1. Can I have 1p? Can we have a 1p orbital? Yes or no? Absolutely no. Why? Because 1p, which means n equal 1, L equal 0. Got it. That is not exist. 1p is not exist. Okay, now see px, py, pz, ml. ML is about what? It is orientation, right? ML is the orientation. The p orbital, you have 3 orientations. So this one is a px. This one is a py. This one is a pz. Can you tell me this one positive or negative? Positive or negative? That is a positive. Here it's a negative. Here is a positive, here it's a negative. Here is a positive, negative. Do the math. How? Let me show you. Here's a 0, right? This is y. Here is x. Do you think here is a plus? Plus. Here is what? It's a minus plus. Here is a minus minus. Here is plus minus. Right? So see. And this one is a plus. This one is a minus. And you said, why? Why we need to know that? We are going to use orbital, make a chemical bond. In a couple of weeks, we are going to make a chemical bond. And only plus plus, you make a chemical bond. Minus minus. And plus minus, you will not make a chemical bond, such as plus 5 minus 5 equal what? This plus 5 minus 5 equal what? Uh-oh. Uh-oh. Equal 0, which means it's a node. It's a node. Equal 0, it's a node. Got it. Equal node is node. That's why. Remember the sign. Okay. Remember the sign. See? Here, red. In this picture, we use the red color as the plus sign. The blue minus. But remember, S, there is no plus minus. S, no plus minus. Or we treat it as a plus. But P, D, yes, have a plus minus. F, it's so complicated. We are not going to pay attention F, okay? Cool, huh? So I want you to remember that's the shape. That's the shape, okay? That's the shape. It's the p orbital. We are going to use it. We're going to use it. Okay, now let's go detail. No 1p orbital. 1 is 1s. P beginning 2p. You have 2 lobes separated by what? By a node. Here is a node. Yellowish, that's the node. For p orbital, 3 orientation, px, py, pz. And see, p orbital function. You see, and that is a wave function. If we did solve Schrodinger equation, we should get a px, py, pz. No, forgot it. You do not need to memorize. Oh, you get this one, this one. No. Here I just give you some idea. Okay. Now give me a couple more minutes. We are done. Okay. D. What's the d orbital? What's the d orbital, please? It's L equal to how many d orbitals? And that should be ml minus 2 minus 1. Oh no, yeah. 0 plus 1 plus 2, 5. 5. And that 5 orbital here, see? Did you see? Did you see the sign? dxz 没什么 ？Yeah, dxz, dyz, dxy, dx square, y square, dz square. And d orbital have a sign 2, see? Plus, plus, minus, minus, plus, plus, minus, minus, plus, plus, minus, minus, plus, plus, minus, minus, plus, plus, minus. Okay? Now, you need to remember the shape of the p orbital. And also, you need to remember the shape of the d orbital. You need to remember it because we are going to use it. We are going to use it, okay? We are going to use it, okay? Yeah, this is easy. This is easy. Now, can we have 1D orbital? Can we? Can we have a 2D orbital? Can we have a 3D orbital? D orbital beginning 3D. Why? Because n equal 3, L equal 0, 1, 2. See, that's the D. Okay. Right. See. No d orbital when n equal 1 and 2. N equals 3, L equal 2, ML minus 2, minus 1, 0, 1, 2. You have a 5, 3D. That's the name. Now, dz square, dx square y square, dxz, dyz, dxy. 5 wave function. 5 wave function. Now, F. What's the F orbital? That one, L equals 3. ML minus 3 minus 2 minus 1, 0 plus 1 plus 2 plus 3. How many? 2L plus 1, 7. And that 7 orbital, very complicated. Do you see? Do you see? Now, you do not need to memorize the shape. I do not know that. Okay. Yeah, it's very complicated. You have F, very complicated, but beautiful, like art. Now, see, no F orbital n 1 equal 1, 2, 3. N equal 4, you have F. You have 7 orbitals. Now, give me 1 more minute. See, what we did? We did n equal 1 is 1s. N equal 2, 2s, 2p. N equals 3, 3s, 3p, 3d. N equal 4, 4s, 4p, 4d, 4f. And when n equal 4, NH all the same. Here's NH. And that's called the degenerate orbital. What means degenerate orbitals? All the orbitals have a same n, have a same NH. We said to be degenerate. Summary. What we did this morning, this evening, and principal quantum number is the size, energy. L is the shape, ML is orientation. We discuss same energy belong to the same shell. We discuss the shell of the subshell of the shell. And we discuss ML is what? It's the number of individual atomic orbital in the subshell. Okay? So here is a summary. Look at S, P, D, F. Okay, any questions so far? Well, I'm going to stop here. Class stop here. We accomplished a lot today. I'm going to send you homework. You review first. Sunday, you are going to take an exam. Sunday, take exam. There is no office hour, okay? Good night. Bye now.
Bye.